Hello, this is Mrs. Aslenbaum. This is the first of several videos about covalent bonding. So covalent bonding we're going to see involves bonding between nonmetals and nonmetals. So we're talking about the atoms in green on the right side of the periodic table. Up to this point we have talked about bonding between metals and nonmetals, which is ionic bonding. And we have talked about bonding between metals and metals, which is metallic bonding. Now, when we talked about the way that metals react, we're always going to remember that metals are losers. What does that mean? Metals lose electrons really easily. They do so because they have very low ionization energies. It doesn't take a lot of energy to remove an electron from a metal atom. Well, nonmetals do not lose electrons. They gain electrons because nonmetals have much higher ionization energies. It takes a lot more energy to remove an electron from a nonmetal, and they also have high electronegativities. And so when nonmetals react, they tend to gain electrons. If they react with a metal, they can just take an electron from a metal. But we're going to see that when they react with other nonmetals, nobody wants to give up an electron, so they're stuck sharing. Now, when we were talking about ionic bonding, we mentioned the octet rule, which is that atoms want to get 8 valence electrons. That's the driving force behind all bonding. Metals on this side of the table do it by losing electrons. Nonmetals on this side of the table do it by gaining electrons. Okay, so why is everybody trying to get 8 valence electrons? 8 valence electrons represents a noble gas electron configuration. It represents a full S and a full P shell. It's the most stable electron configuration. When we're talking about covalent bonding, nonmetals, when they form covalent bonds, are also trying to get 8 valence electrons. But as we just talked about, they can't do it by losing them. They can't do it by taking it from other nonmetals, so they're stuck sharing. The only exception to the octet rule is going to be hydrogen, which only needs 2. The reason why hydrogen only needs 2 is that it is trying to fill the first principal energy level and look like helium, and the first principal energy level only holds 2 valence electrons. So let's try to model some bonding between 2 hydrogen atoms. So here is hydrogen. Hydrogen is atomic number 1. It has 1 electron, 1 valence electron. So we're going to give each of these an electron. When 2 hydrogen atoms get together, they each have 1, they both want 1. But they have the same electronegativity, and they have the same ionization energy. So they're not going to be able to take an electron from the other one. So if you can't take it, you're stuck sharing it. We can represent that sharing by using circles. You can imagine that this hydrogen atom is going to share an electron with this hydrogen atom, and this hydrogen atom is going to share an electron with this hydrogen atom. Where those circles overlap, that is our covalent bond. And so we can represent the hydrogen atoms like this. We could also represent the hydrogen atoms sharing a pair of electrons by drawing a line. Here is another model picture showing how we could represent the bonding in hydrogen atoms, where we're using Bohr diagrams to represent that they are sharing a pair of electrons, thus filling that first principal energy level. So covalent bonds occur between nonmetal atoms, and the atoms are held by sharing electrons. Turns out that because they're actually sharing, as you can see, they're actually connected. And so this is a much stronger bond than an ionic bond or metallic bond. This is the strongest of the 3 bonds we've talked about. So a covalent bond occurs between nonmetal atoms and involves the sharing of electrons. Now, we got to talk about a few terms. For the first time, we're going to use and describe what the term molecule means. Molecule refers to a covalent compound. Those 2 words are used interchangeably. Molecule also refers to a neutral group of atoms. So we're going to see that if you've got something, you can have nonmetals that are covalently bonded, but if they have a charge, we refer to them as polyatomic ions. The diatomic molecules, we've mentioned them already, but these are elements that are always found as two atoms covalently bonded to one another. The way that you can remember them is that there are 7, and they make a 7 on the periodic table. So they include nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and hydrogen. Another way to remember them is the little term Brinkel-Hoff. Okay, Brinkel-Hoff is for bromine, iodine, nitrogen, chlorine, hydrogen, and oxygen and fluorine. So these are elements that whenever you find them in nature, they will always be combined as two atoms bonded together as a molecule. Now that we've kind of talked about the octet rule, we can actually look at these and start to understand why that is the case. So let's start with fluorine. Fluorine is in group 17 periodic table. So if we look back at fluorine, here we are, group 17 in the periodic table. It has 7 valence electrons. So we're going to give each of these fluorine atoms 7 valence electrons. But how many do they want? They each want 8. So we can see that if this fluorine shares 1 electron with this fluorine, and if this fluorine shares 1 electron with this fluorine with a covalent bond, then they can each achieve their stable electron configuration of 8 valence electrons. And so fluorine is much more stable when it is F2, 2 fluorine atoms covalently bonded to each other, than when it is just F by itself, because now it's got 8 valence electrons. Let's look at oxygen. Oxygen is in group 16, so it is going to have 6 valence electrons. So here are 2 oxygen atoms, each with 6 valence electrons. Now, they also would each like to have 8. So what can happen is that this oxygen can share 2 electrons with this oxygen, and this oxygen can share 2 electrons with this oxygen. What we see here is that this time they're going to share 4 electrons, or 2 electron pairs, in order to get their stable octet of 8. And oxygen is much more stable when it's bonded to another oxygen as O2 than when it is just an individual oxygen atom all by itself. Okay, so we talked about the fact that molecules are neutral atoms, but you can also have nonmetals bonded to nonmetals that are covalently bonded to each other, and then the entire compound loses or gains electrons. These are what are referred to as polyatomic ions. So these are electrically charged collections of nonmetal atoms bonded to each other. And you can draw an example. This here is called the phosphate ion. We would write its molecular formula as PO4 3-, and it involves a phosphorus atom covalently bonded to 4 oxygen atoms, but the entire compound has a charge of -3. This here is called the ammonium ion, NH4+, and it involves nitrogen covalently bonded to 4 hydrogen atoms, and the entire compound has a charge of +1. Your reference table E, lists selected polyatomic ions. So whenever you want to know the polyatomic ions, you're going to look to reference table E. And you can see there is a whole bunch of them, and they give you the name for them. Whenever you have a compound, and this is important, that contains polyatomic ions, that compound therefore contains both ionic and covalent bonds. So in order to recognize something as containing both ionic and covalent bonds, so in order to recognize a compound as containing both ionic and covalent bonds, you really need to be familiar with your polyatomic ions. Anytime you see a polyatomic ion in a compound, it contains both ionic and covalent bonds. To illustrate what this looks like, and this is what you'll be drawing in your note packet, this is the compound sodium carbonate, Na2CO3. This is the carbonate ion, CO3 2-. The carbonate ion is held together by covalent bonds. So these lines holding the carbon to the 3 oxygens, those are covalent bonds. This entire ion is then ionically bonded to the sodium ions. So these are ionic bonds. This compound contains both ionic and covalent. And any time you have a compound with a polyatomic ion in it, it contains ionic and covalent bonds.